Hello everyone. In this video I'm going to show you how you can perform different types of analysis with Fractalis. For the purpose of this demonstration I selected a paper from Nature Communications where the authors performed different types of analysis based on a publicly available dataset. They created several charts and performed different types of analysis, and we use their results as a comparison for the results we get with Fractalis to have clear use case and to see that Fractalis actually performs well and doesn't, make up any data. All the information that I'm going to use in this video are available in the description below this video. Make also sure that you check out the other videos I recorded previously and that I will probably record in the future, because they show different types of functionality in Fractalis and they show different integrations, things that I cannot all cover within a single video. Also, all materials related to Fractalis will also be always available on the homepage of Fractalis. For this, you just go to https://fractalis.lcsb.uni.lu. And there are several links, and the page might change, but all information will always be available on this webpage. The paper that I mentioned earlier is Nature Communications paper. The content of that paper is not that important for the purpose of demonstrating the functionality of Fractalis. What is important is what the authors have done in figure 1. If we zoom in here, we see that the authors performed a volcano plot, so a differential expression analysis based on the microRNA data of this dataset. They performed a MA plot. They performed a box plot with a group test, so probably ANOVA. And they performed a survival analysis, or more specific, Kaplan-Meier analysis. Figure D and F will be ignored in this demonstration because they are from a different data set and they aren't all that interesting to showcase different functionalities of Fractalis. So we will focus on A, B, C, and E of figure 1 of this paper. Before I start, I should mention that this paper is from 2015. The authors did not very well disclose the methods or the parameters that they used in this analysis. So we will have to experiment a little bit. Also, the dataset itself from TCGA grew in the last couple of years. There is now, I believe, roughly 460 samples, and that's roughly 50 or 60 samples more than in 2015. So the results that we will get with Fractalis are probably roughly similar, but they will not be exactly the same because we don't know what the authors did with this data more than having just a general idea of the analysis they performed. Also, we do not know which samples were included at that time in the dataset. The dataset itself, it's completely public. You can go to the NIH CDC data portal and you can just download all of it. So this is completely public. So let's begin. We go to the webpage fractalis.lcsb.uni.lu. We press on demo. On this webpage you can see not much. You see some description here. You see a couple of controls. What is very important to understand is that Fractalis is a library. Fractalis is not a user interface, nor is it a standalone service. So usually Fractalis would be, as you can see in this video, which is a previous video in the playlist, Fractalis would usually be in another service. So functionalities as cohort selection or subset selection, for instance, case versus control, early stage cancer versus late stage cancer, this type of selections and also the data selection itself would be provided by the user interface. Fractalis on its own is just a visual analytic platform. So you can create charts which are backed by a powerful analytical engine. For the purpose of this demonstration, I loaded some data into Fractalis. Usually this would be done via the supporting service, so Transmart, I2B2, whatever platform. So in order to recreate or create the charts that we have seen in the paper, I will select volcano plot from this drop-down menu and I will press Add Chart. And you will see that there is a control panel here on the right side with the microRNA data preloaded. There is also a couple of other data. So for instance, if we would select scatter plot, you see that there is also a couple of clinical data. So year of birth, the days to death, and categorical variables like tumor stage, race, gender, this type of thing. But we only want to create a volcano plot for now. So we create a volcano plot, and the authors mentioned in the paper that they used DSEG2, that's an R package that performs a differential expression analysis on count, so quantification data, so integer, not floats. The default settings should be fine. So on our x-axis, we use the log fold change, and on our y-axis, we use the negative log 10 of the p-value. The minimal total reads is 10. We have over 400 samples, so you can probably set this value quite a bit higher and still get very good results. But 100 is enough for now. So let's press this button, and you see that we now selected everything that's necessary for analysis to start. The differential expression analysis is very expensive. This analysis right here happens on many different CPUs because it's parallelized, but it still takes a moment to compute all of the rows and all of the samples that are in this data set. And we see pretty traditional volcano plot with log fold change on the x-axis, the negative log 10 of the p-value, and the real values on top and on the right side. So what we can do now is we can select, so with the mouse, by clicking down and dragging, we can select a certain area. And what we are interested in is the area from, let's say, the p-value should be at least 0.001 and a log fold change of at least 1. So we are looking now for upregulated significant genes or micro RNAs. So we select this area, and we see two different microRNAs that are within this area. That's one time the MIR 1269 with isoform A, and the MIR 187, both with pretty high significance and a rather large log fold change. So if we have a look here, you see that the plot is actually quite different. So we aren't quite sure what the authors did to create this plot, because if you plot the log fold change against the negative log value of the p-value, you usually end up with a volcano-shaped plot, hence the name volcano plot, whereas this doesn't look at all like a volcano plot. So they probably did some sort of pre-processing or post-processing in order to achieve this kind of plot. You might argue that they used a negative log 2 and we used negative log 10, but this doesn't change how the data looks, it just changes the numbers on the axis. So as you can see, when we select negative log 2, our numbers change, but the plot still looks the same. So that can't be it. Nevertheless, we see here the same microRNA that they found. Now, the second thing they did is a MA plot. That's this thing here. And the reason for doing this is, if you are interested not only in knowing whether my whether these microRNAs are significant, but whether they are here in a certain quantity. Because if you look at the data, you can have a lot of very, very small read counts. And if they are close to zero, so you have maybe 1, 2, 1, 3, 4, and then your comparison set, so high stage or late stage cancer in this case, has 10, 20, 15, 7, 8, then this can already be very significant, but this is really a very this is very low quantity, very low data density. So that's the reason why they did this MA plot here. And we do the same. So we select volcano plot again because, interestingly, the statistics for MA plot are exactly the same than for volcano plot because we have to do a differential expression analysis again. So we select again DSEC2, select a minimal total rate of 100, but this time we select as a x-axis the log 10 value of the base mean and the log 2 value of the fold change for the y-axis. So let's do this. That's log 10 of the base mean and log 2 of the log fold change. Yeah. And we start the analysis. You can also track this field around and you see how your selection changes. But that's not so interesting for now. So we have to wait a little moment here until the analysis is done. And here it is. So what we see here is the following. In the upper right corner, you would see the microRNAs, which are upregulated. And on the right side, you would see your microRNAs, which are here in a large quantity or a larger quantity. So similar to the left side here, we will select everything that has a base mean of 10 and a log fold change of 1. That's here. Where is this? Oh, I actually did the log 2 of the log 2 fold change. So what we actually wanted to do is we want to choose the identity of the log 2 fold change. Yeah, that looks much better. The reason for this is that for this strange name CR, this is exactly the output that is generated by the DSEC2 package. So this is the statistics that come from the server side, and you can pick here what you want to select. And you see here, because the computation has already been executed, we can now pick between the statistics that we want to see. So let's try this again. We go here. We are interested in everything with a base mean higher than 10 and everything with a log fold chain with a log 2 fold change higher than 1. We select this area here, and we see something really interesting here. We have again 2 microRNAs, but if we intersect our selection with what we have here on the left, only this 1, 2, 6, 9 microRNA is in both of these sectors, which is exactly, or not exactly the same, but which is a good indication that what we are seeing here right now and what the authors of this paper saw are the same. Now that we have figured out or found a microRNA of interest, we can put it in a box plot and see whether there is a significant difference between early stage cancer and late stage cancer. So we can select a box plot here. And now you might ask yourself, how do I select just a single feature out of this matrix of data? Fractalis makes this quite easy for you. So you can go, you click here on the right side, and there are several options available. None of which are very interesting right now, except of this add filter. So here you can, you have a fuzzy match. So you press or you type 1, 2, and you see there is a couple of options that are offered to you. But we know exactly the one we want, so we press 1, 2, 6, 9, and we see that are the two isoforms for 1, 2, 6, 9. But we are interested in isoform 1, 2, 6, 9a. So we click this, and now we selected a filter. Now we click this variable, and we see two box plots. Now these box plots look a bit strange. And the reason why they look so strange is that there is probably a lot of outliers in the plot. So when we click here on the checkbox in the control panel, show points, we see there is a lot of red points, whereas the black ones are where the box plots are. That means there is a lot of outliers which go all the way up to 9 or 10,000. So if we deselect this button, we see that the box plots, they look much more reasonable. But still, if we go to the paper here, we see that there is quite a difference between what we see and what they see. Here, the box plots go from 0 all the way up to 4, maybe 5. Whereas here, let's take this control panel on the side, whereas here they go all the way up to 600 or 700. So there's quite a difference. Now, we assume that it's very likely that the authors applied log transformation to the data. So we will do the same here, apply log 10, and we see exactly the same than the authors do. So we see here that the left box plot goes a little bit less than 4 and the right one goes all the way up to 4. We see also that there is a p-value, a significant p-value for the difference between these two groups. So what Fractalis did here was it performed a one-way ANOVA on these two box plots, and it came up with a f value of 7.4 and a p-value of 0.006897. This is quite a bit better than what we see in this paper here. There, the p-value is noted as 0.01. That's likely because we have quite some more samples since the data set we use here is a little bit older. So that's probably why this p-value looks so much better. Okay, so what we did so far, little recap. We looked for interesting microRNAs. We found one, we put it in a box plot, and now we see that there is indeed a difference between early and late stage cancer for this microRNA. These two groups, they are, by the way, denoted as S1 and S2, so these are the subsets that have been pre-selected prior to this video. Now we have to create one more plot, and that is this survival plot. In order to do this, we will rearrange this layout a little bit. So we will deselect this, make this a little bit bigger, maybe a little bit smaller than this. And we will create a survival plot. Here, this is our empty box for survival plot. Now we go here. And we see a couple of boxes. So we can select the duration. So in our case, this is days to death. And we see here a survival plot. Now, this is pretty much what we would expect, because right now there is still these two subsets selected with early stage cancer, with late stage cancer. And it's pretty obvious that, let's take this away again, that for the late stage cancer, so days to death, subset 2, that's the orange one, that these patients have a much worse survival curve than the one with early stage cancer. Also should be noted that in these days to death, there is obviously only the samples which have a recorded death date. So we essentially do not take into consideration any samples at this point without a recorded death date. But this is not what we are interested in right now. what we are interested in is whether the microRNA that we found has a predictive quality to it. So whether there is a relation between the survivability of the patient and the level of this microRNA. So what we can do is we can press this little checkbox, ignore subsets, which will automatically undo for this chart the subset selection that we have done prior to this video. The second thing that we want to do now is we want to compare high versus low read count levels of this microRNA. This is usually something that would be provided by the parent user interface or by the platform that Fractalis operates in. So what we did now is we pre-created this variable for the purpose of this demonstration. So this categorical value here separates patients to the group with a read count level of this microRNA higher than 1,500 and lower than 1,500. This is an arbitrary value that sadly was also not disclosed by the authors, but it roughly splits up the samples into these two groups that were mentioned in this paper. So let's do this. And we see here that the group with a high read count has roughly half of the survivability than the group with a high read count. Now, this plot or this chart here is not very conclusive because, as you see by the very large confidence interval for the group with a high read count, there is a very strong overlap here. And this group is also very, very small. I believe there is only 10 to 15 patients in it. But this is also the case for the survival plot in the paper. Also, I believe that the authors of the paper, they used the entire population. So both of these charts include not only, or both of these lines here include not only the patients who died, they also include the patients who are still alive. But I believe there is still, if we compare these two, we still see that we come roughly to the same conclusion, that the high expression level of the microRNA 1269 has an impact on the survival time of the patient. Okay, this concludes the video. You have seen here a very small snapshot of the functionality that Fractalis has to offer. There is many more features, such as the recomputation of your plots depending on your selection, and also a lot of buttons that I didn't click. So for instance, this one, and also a couple of other things that I didn't show. But I believe this demonstrates how you can perform explorative analysis in a very dynamic fashion with Fractalis. Also, in whatever I did today here can be done with the data that are available on the demo page of Fractalis. In fact, this is not running on my notebook. This is running, I did this entire video on the publicly available URL that you can see here. So you can go right now to this webpage and try this for yourself if you want to. Also, make sure to contact me if you have any questions, if you see any issues. I'm usually quite fast to respond and quite fast to fix issues if there are any. Well, thank you for listening so far, and see you in another video.